Hi, hello students. Welcome back to India's most comprehensive online learning platform, Byjus Exam Prep. This is Anil Prasad Sorumpudi, and in this session, we're going to have a complete look at the revision of the operating system. And that too, since I'm getting the request from many of the students to revise the topic of the synchronization, I will focus more on synchronization. So, since tomorrow is your exam, I will just take up the important topics of the operating systems. That is, first I will start with the process scheduling, then synchronization. Okay, so we will start with the operating systems basic topics, then process scheduling, and then followed by synchronization. If you do have any doubts, I request you people to ask me in the chat box. So let us start the session without wasting any more time at all. So first of all, please confirm, am I completely audible and visible? Am I completely audible and visible? Somebody please let me know, am I completely audible and visible? Mark your presence so that we will start. Yeah. Hi, Puvas Rasan. Okay, fine. We will start, and if you do have any doubts, I want you people to ask me instantly. Hi, Shavik. Very good morning. Let us start this session. Okay. Now, first of all, before starting the things, before any proceeding, this is about myself. This is Anil Prasad Sorumpudi, and I'm a triple PG holder. Is the screen clear? Of course, screen is very clear. I think screen is clear because I do have a very fast internet connection, broadband connection. Please let me know if you do have any problems, technical problems or technical glitches that you're facing. Please let me know. If that is from my side, I'll be able to resolve. Otherwise, just need to check up at your end. Okay. So, is the screen completely visible? Is the audio clear and video clear? If you can confirm, we will go ahead. But meanwhile, this is about myself. This is Anil Prasad Sorumpudi. I do have a total of 13 plus years of experience, and I am a triple PG holder. I did my MBA, MSc in Information Technology. I also did my MSc in Mathematics. Audio not clear? Just a minute. Hello, hello, hello. Is my audio clear? Now, is my audio clear? Please let me know if my audio clear. Saurvik Purvasan, is my audio completely clear? Okay then, fine. Okay, let us start. Yeah, first of all, this operating system concept will start exactly from the point of the process. The total entire operating system can clearly be started. The starting point will always be the concept of process. Why? I'll tell you the fundamental reasons behind to start the operating system concept with the concept of process. See, operating system is an organizer of the computer system. Computer system essentially is a collection of hardware units. We have a CPU, we have the main memory, we have the IO devices, and this total computer system is used for the purpose of program execution. If you want to use the computer system, you can only use for one and only one purpose, that is program execution. The computer system should be able to execute the programs. Now the thing is, what is the job of the operating system? Operating system should create and provide an effective environment for the program execution. The program can be called from the operating system's perspective, in the operating system's technical words, as a process. That is the reason why The operating system concept exactly starts from the concept of a process. Let us understand what exactly is this process concept and how we will be able to move forward from the process concept, covering all the important concepts of the operating system for tomorrow's exam. So let us stay focused. First of all, when you talk about a process, this process is just nothing but a program that we are executing. Process is just nothing but a program. What is a program? A program is a set of instructions. But do we have any difference in between program and a process? Yes, we do have. That is, a program is just a collection of some instructions. But when you talk about a process, that process can be referred to as the program which is in the execution. When you say, if you have 100 programs, all the 100 programs are not needed to be executed concurrently. Only those programs which are being executed concurrently right now in the system at this point are called as processes. So, a process is an active entity, a program is a passive entity. And the real difference between a process and a program, I will tell you. Now the thing is, when it comes to a program is simply a text section or a collection of instructions. But when it comes to the process will have 4 sections. Yesterday I told you, the process will have 4 sections in the main memory. When a program becomes a process, the program should get transferred to the main memory. As it goes to the main memory, it will be allocated with 4 regions. What are those regions? The first one is the text region or a text section. Second one is the data section. Third one is the stack section. Fourth one is the heap section. All these together to be referred to as a process. In the text section, the instructions of the program will get transferred. In the data section, the global variables of the program will get transferred. And the stack section, local variables will get transferred. Heap section, dynamic variables will get transferred to. Okay, so this is the process. Process meaning the program which is in the main memory and it is ready for the execution, which is called a process. This is how a process looks in the memory: text section, data section, heap section, and a stack section. Now, when you talk about a process, that process can be any of in these states. A process is expected to be in one of these states. Understand the life cycle of a process. The moment a process is created, till the moment it just is terminated, the process will go through several phases. All these phases will come under the umbrella of the life cycle of a process. Okay. Is my voice low? Why my voice is low? Is it clear right now? I don't know why my voice is very low. Just a minute. I will check it out. Why? The same I'm using. Hello, 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 hello. Is still low? Huasan, is my voice still low? Clear, right? Arjun is complaining that my voice is very low. Please, somebody, let me know. My voice is clear, right? The other people. Pranesh, Lokesh, please, is clear, right? Yeah, the settings are the same. I did not change any settings, so it would be the same as yesterday. Okay, so let us start. Let me right from the moment the process created till it gets terminated, the process will go through a lot of phases. What are those phases? First of all, the first state of the process is a new state. The process is just being created, meaning understand the transformation of a process from a program. Let us say this is your hard disk. Okay, after the hard disk, we do have something called main memory. Then the programs which are in the main memory will be selected by the CPU for execution. So understand, initially, when the computer system is switched off, all the programs are resorted back to the hard disk. Now, when you switch on the system, the programs which are needed to be executed right now will get transferred from hard disk, secondary memory, to the main memory. The programs which are transferred to the main memory can be called as processes, because in the main memory we are going to allot or allocate 4 sections: text section, data section, stack section, and a heap section. Right after they got transferred to the main memory, the programs are eligible for execution. Then the CPU will select those programs in a specific order for execution. Now, the moment the program gets transferred to the main memory till it leaves, the program is expected to be in any of these states, starting with a new state. New state meaning the program just is transferred from secondary memory to the main memory. Next new state will be followed by the ready state. This is the second state. Okay, ready state meaning the program now became a process and it is ready for the execution since it is stored in the main memory. And the third one is running state. After a program is transferred to the main memory, sooner or later it will get selected by the CPU. The moment the CPU selects this program for execution, and as it is executing, this program is said to be in a running state. Right after the running state, the program may go to waiting state. For an example, your C program may require to execute a printf statement. When the printf statement is being executed, your C program should go out and wait at the monitor, because monitor is not a part of the CPU. Monitor is an output device. Printf statement requires some data to be published on the monitor, printed on the monitor, for which your process or the program should wait for the response of the monitor. Soon the monitor responds, your program will be able to print whatever the desired data onto the screen, for which the program needs to leave the CPU and wait at the monitor, which is an IO device. So every program, after executing for some time in the CPU, it will go to perform some IO operation. Since the IO devices are not the part of the CPU, since the IO devices are the external devices, a program needs to go out of the CPU and wait at the IO device, and the moment the IO device responds, it is going to perform the IO operation and will return back to the CPU for execution. Okay, and then ready state. Ready state meaning, as I already told you, ready state meaning the program which is in the main memory is said to be in the ready state. The next thing is, I already told you, the terminated state. What is the terminated state? Terminated state meaning when a program is completely executed, the operating system will terminate this program. What exactly do you mean by the termination? When a program is executing, the operating system will allot a few resources. What are the resources of the system? I am a program. I want to execute. I will request the operating system to allocate me the resources that I need. Sir, please explain me what are the resources. I will let you know what are the resources. The first resource of the system is CPU time. Any program, when it wants to execute, it requires a specific amount of the CPU time. And the operating system should be able to allocate the desired CPU time to every process. Second thing is main memory space. As I already told you, if you want to execute a program, that program is expected to be in the main memory. The program should be made available in the main memory, without which the program can never execute. So main memory space should be allocated to any program which wants to execute. And the third one is IO devices. What is the IO device? Several, for example, your C program frequently often needs to print some data onto the monitor, right? Monitor is the only IO device that is required by your C program, in addition to your keyboard and the mouse. Your C program also needs to take the inputs from your keyboards and mouse. So every program during its execution may require several IO devices. Operating system should take a call which IO devices should be allotted to the program. And finally, one of the most important resource of the computer system is the file system. Okay. During the execution, any process needs several files. For those files, it may request the operating system. The operating system, depending on the availability of the files, because understand carefully here, I am the operating system, you are a program, you requested me for a file. Since the file is a common resource, the file cannot be allocated to more than one person at a time. So I will see if the file is available. If the file is available, I'll allocate. Otherwise, I will keep you in the waiting state. I hope you got the point. So these are the resources that are requested by or required by the program at any point of period. So these are the resources which can get allocated to any process depending on the availability. Here the boss is always operating system. Operating system will take a call either to allocate a resource or to deny a request. When I'm a program, I will make several requests. I want a CPU time, main memory, IO device in the file system. There is no guarantee that you are going to meet your request. You're going to be provided with all the resources that are required. If it is not available, what operating system can do? Let us say main memory is completely full. You want to execute, operating system will hold you on because there is no space in the main memory. If one program goes out, then you are admitted into the main memory. Right, then during the execution you wanted a file, but the file is already consumed and occupied or used by some other program. Can that file be allocated to you? No. So the operating system needs to take a call whether to grant a specific resource which is requested or to deny the grant to the access to the specific request. I hope you got a point. Okay. So these are the resources of a process. Any process during the execution, it will be allocated with these resources. Right, then the process state. This is the state diagram of a process. Understand how it goes. Initially, any process will start from a new state. Right from the new state, it will go to the ready state, meaning it is getting transferred to the main memory. The moment it is completely available in the main memory, it is waiting for the CPU. I am the process. I went to the main memory. What is my job? To sleep there? No. I'm waiting for the CPU time because CPU is not available at that point. CPU is not free to admit me immediately. There are several programs that went into the main memory prior to myself. So according to the priorities, according to some rules and protocols, I will definitely be admitted at some point. But meanwhile, I need to wait in the main memory, which is called ready state. A program which is sitting in the main memory for the response of the CPU, for getting admitted into the CPU, is said to be in the ready state. The moment a program is provided with the CPU's time, the program goes into the CPU. Then a program is said to be in the running state. What is the running state? When a program is executing in the CPU, that is called a running state of the program or a process. Okay. After the running state, when a program executes for some time in the CPU, it may go to perform some IO operation. Since the IO device is an external device, program needs to go out of the CPU, will need to wait for the IO device to respond. The moment the IO device responds, the program will perform the IO operation. Right, then it will come back to the ready state. After performing the IO operation, it will come back to the ready state. After performing the IO operation, no program is entitled to go back directly to the running state. I'll tell you why. When you leave the CPU to perform some IO operation, one more program will be sent into the CPU because CPU's time is always vital. CPU's time is always important. It cannot be wasted. CPU's time is always holding the greater significance. It can never be wasted at all. So the moment CPU is free, immediately the operating system will schedule one more process into the CPU. So the process P1 goes to perform an IO operation, then immediately let us say a process P2 will be scheduled into the CPU. So the process P1, when finishes with the IO device, it cannot directly go back to the CPU because process P2 already is in the CPU. So for which P1 will go back to the main memory, which is said to be the ready state. From the ready state, again it will go to the running state. Okay. So what is this terminated state? Finally, with one final execution, let us say I am completely finished. All my instructions are completely executed. So what you're expected to do? You're expected to be terminated. You just start terminating. Okay. In the terminated state, what exactly is going to happen? Termination meaning we're not killing anything physically, but terminated state meaning upon the completion of a program, the operating system will relinquish the resources that have been provided, will collect those resources back. Simple. For a program P1, I gave several resources. Now P1 completely is executed. Now I will take my resources back because these resources will be added to the total pool of the resources and can be allocated to any other program which is created right now. So upon the termination of a program, operating system will collect all those resources which were given earlier to this program. So that is called a terminated state. Any resource that is allocated to a program, which is the reusable resource, can be collected back by the operating system at a terminated state. Now, what is a process control block? Understand carefully. In order to understand the process control block, let us understand. When you join in a college, see, you will have your own ID. At different places, you will have different IDs. At your home, you will be called by your name. At some other institution, you will be provided with an ID, and by using that ID, you will be represented with. When you go to a college, of course, definitely you will have an ID. But in the college, essentially, a record will be opened for you. On your name, a record will be opened, right? Because it is highly impossible to point a boy or a girl when they are studying. But in order to maintain your status, in order to maintain your updates, every college, for any student, it is going to open a record. The record contains all the details that are necessarily to be maintained for award for a student. Maybe the student ID, what is his pass percentage, and in which year he is. All the details that are needed to be maintained for a student will be maintained in this record, right? Similarly, for every process, upon its arrival, the operating system is going to open a record. This record is called something called a process control block. This process control block is available in the kernel section of the operating system. Do you know the kernel section? Of course, at this point, I know it is a foolish question, but still, the questions always are foolish, as I already told you yesterday. Do you remember? Hi, Elon Musk. I guess it's quite some time to see you. Good to see you back. First of all of you, please let me know, have you heard about this kernel portion of the operating system? Okay, first of all, respond. It's just not I teach, you learn. Make it as an interactive session, as much as possible. Okay. Respond somebody, Lokesh or Arun, Arjun. I do have 20 people with me. Everyone should respond. Yeah. Have you heard about this kernel portion? Very good. I'll tell you anyhow. I'll tell you exactly what exactly is this kernel portion. Operating system, when it is created, when the system is loaded, I'm going to, privileged mode, fine. Kernel portion is not privileged mode. I'll tell you what exactly is this privileged mode. In the privileged mode, the kernel section code will get executed. Kernel section is not the privileged mode, okay? In the privileged mode, the services which are stored in the kernel will get executed, such as printer. I hope you got the point. Anyhow, operating system will be loaded in the main memory in these ways. Operating system will be divided into 4 logical sections. The first one is the kernel section. Second one is system programs. Third one is application programs. And the fourth one is user space. What is the kernel section? Initially, when you switch on the system, initially the kernel portion will get loaded. What is kernel portion? Kernel portion meaning it's a collection of services. What is there in the kernel portion? Simple. Kernel portion is a collection of services. There will be hardware services, software services. What are the hardware services? Hardware services meaning your service routines to access all the IO devices, maybe printer, maybe scanner, maybe keyboard. In order to access every IO device, there has to be a specific code get executed. That code is available in the kernel mode. That code is available in the kernel section. And what are the software services? Cut, copy, paste. What is the cut, copy, paste? Cut, copy, paste are the features that are provided by the operating system, which are not directly written by you. You don't know what is the code behind it. These are called system calls. System calls are the software services. So kernel portion essentially is a collection of hardware services, software services, and kernel also provides some basic data structures, free empty basic data structures, which may be required by a program in the near future during its execution. Understand carefully, kernel, you in several times you may have coined this the word kernel, but what exactly is this kernel? Is this like, Brahma Padartha? No, it is not rocket science to understand a kernel. Kernel is a collection of software services which are otherwise called as, the system calls, hardware services, your service routines, and some data structures, some empty data structures. These data structures may be required by the programs during their execution. Are we clear so far? Are we clear? Very good. So, what is the PCB? PCB is a customized data structure, okay? Understand carefully, when the system is switched on, PCB is the data structure, empty data structure. There are several PCBs. Am I clear? It's the customized data structure. Customized data structure meaning it's a collection of several data structure, arrays, maybe linked list. Of course, PCB is a collection of data structures. One PCB may be a collection of some data structures. So I can call it as a customized single data structure. Now there are 1000 PCBs in the operating system right now. When I switched it on. Initially, when I switch it on, all these 1000 PCBs are empty. But these PCBs will be allocated. The moment a process is created and available in the main memory, I will allot one PCB to it. In that PCB, the information that belongs to that process will be maintained. Am I clear? I hope I am. I want you people to respond. I don't know. Do you understand what exactly is this PCB? Or do you have any doubts? Okay. Now, what will be maintained in the PCB? The PCB meaning, first of all, in the PCB, there is something called process state. Process state will be maintained. Which state the process is in. And then program counter value. What is the program counter? Next instructions address. When a process is executing, program counter will store the next instructions address. That will be maintained. CPU registers. When a program is executing in the CPU, it uses several registers to store some values. All the values of the CPU registers will also be stored in your PCB in the main memory. CPU scheduling information. Yeah, that is what I'm saying. PCB is simple. PCB is a record, I would say. This record, let us say initially it is empty. Let us say a process P1 arrives into the main memory. This PCB will be allocated to process P1. So, whenever process P1 is executing, this process P1 data will be maintained. The status will be maintained within the PCB. What exactly are the things that are stored in the PCB? Process state, in which state the process is currently in, program counter, what is the next instruction address of the current program, CPU registers, what are the values that are present in the CPU registers as it is executing, CPU scheduling information. Now, what is the order of this process? What is the position of this process in the scheduling? I'm a process. Right in front of myself, there are several other processes. I cannot directly get into the CPU, right? Definitely there will be a few more processes that are waiting to get into the CPU. So definitely I will hold my position. My position is 5th position, let us say. So I will be able to enter into the CPU only after the first, my pre-sequent 4 processes are executed, completely gets executed. Then only I'll be able to be admitted into the CPU. Then main memory management information. The memory management information meaning, in the main memory, what is my space? Because when I'm stored in the main memory, I'll be stored in a respective location, specific location. I cannot use the total main memory. For an example, my location is from 300 location to 400 location. So my base address is 300, my final address is 400. So I will only be able to use these addresses of the main memory. So main memory management information should be maintained within the PCB in order to avoid any chaos, because during the execution, I cannot access some other's address space. I cannot access some other's memory space. This is the very reason why this memory management information must be maintained accordingly within the PCB. And the next thing is accounting information. Accounting information meaning when a process, let us say the process P1 has been created. Now this P1, during the creation, it will admit the total required time of the CPU. For an example, I want 1000 milliseconds during the execution. I'm a process. If I have to finish, I require at least 1000 milliseconds from the CPU. I will admit the operating system will provide me with the total 1000 milliseconds. So every time when I am getting printed, the total time that is used by myself will get subtracted from this 1000 milliseconds. So every time I executed for 5 milliseconds, I came out to perform some IO operation. Rather, I got printed because of the priority. So every time when I go to get into the CPU and coming out, my time will be deducted. I mean, by the total time that is spent by myself. So initially I spent 10 milliseconds, that will be subtracted from 1000. Finally, when this time, the accounting information, the total CPU used, if it becomes 0, this process needs to be terminated, because the total admitted time has actually been met to, has actually been utilized. So this process cannot execute anymore. So CPU utilization will be maintained, and clock time elapsed in start, as I already told you, time limits. This is what the accounting information. This all will actually be related to the CPU used. And IO status information. What exactly is this IO status information? IO status information meaning during the execution of a process, it may require specific IO device, several IO devices. So here in the IO status information, the number of IO devices that are being used by the current program will be maintained. I hope I made my point clear. Because understand, when an IO device has been allotted to one process, that cannot be allotted simultaneously to the other process, because of the property of mutual exclusion. Have you ever heard mutual exclusion? I'm going to give you the complete glance and idea about the mutual exclusion, which is the important aspect of the synchronization. But have you ever heard about this term mutual exclusion? Anyhow, when an IO device is being used by one program, this cannot be used by another program. As simple as this. Okay. Any doubt so far? Any doubts so far? All of you? Very good. Okay then. Okay, right? It's 10:30. I hope everybody woke up. Everybody had their breakfast. I hope everyone had their coffee, and everyone is very active indeed right now. So be with me all the time. I'm going to make all this concept very clear. Very good. Okay. Now, let us enter into an important topic, which is called operations on processes. Okay, I'll tell you that I am actually expecting a question on operating on a, the operations on a process. But before which, let us understand process scheduling. Okay, I'll tell you, I'll very briefly, I'll tell you in a easiest manner as possible. I want people to be with me to understand this concept. See, initially, forget about this. I just will use an empty slide. Let us understand this. See, this is the secondary memory. Okay, assume that this is our secondary memory. Assume that this is our main memory. Assume that this is our CPU. Okay, this is the CPU. This is main memory, and this is secondary memory. Okay. Now the thing is, initially when you switch off the system, all the processes are here. All the processes are here. Since the main memory cannot hold any information when the system is turned off, all the processes are resorted into the main memory. There are several processes, n processes are available in the secondary memory, bigger part. But the moment when you switch on the computer system, you may require to execute a few programs. Which programs will get transferred from secondary memory to the main memory? Who is going to make that decision? Who is going to take that call? So understand carefully. It is not some random process that gets transferred to the main memory from secondary memory. Rather, there will be a specific guy employed for this job, which is called job scheduler. Okay, this job scheduler is the person. Okay, in the technical terms, this job scheduler is a process who is going to select the process that are in the secondary memory, a few processes that are in the secondary memory, and transfer them to the main memory. This is the job of the job scheduler. Job scheduler, when he executes, he is going to select a few processes from the secondary memory and send them into the main memory. So in the main memory, there are several processes. A subset of the process of the secondary memory will be stored. Let us say PK. Pn is the total process that are available in the secondary memory, from which a subset of the process will get transferred to the main memory. Who is going to select this process? My job scheduler. And the second one is something called a CPU scheduler. This CPU scheduler, this guy's job is to select the next process from the main memory and send him into the CPU. Okay, so understand carefully. Initially, job scheduler is going to pick up a few processes, is going to make some selection among those processes. But for this, we need to use some, these schedulers are implemented by using some scheduling algorithm. Maybe shortest job first or longest job first, I don't know. Maybe round robin algorithm. So we are going to use some scheduling algorithms to design the schedulers. Either CPU schedulers or job schedulers will be implemented by using, will be realized by using some scheduling algorithm depending on the system. Depending on the scheduling algorithm, these schedulers are going to schedule the processes. The job scheduler is going to select a few processes. Let us say job scheduler is a SJF scheduler, shortest job first. When it executes, it is going to find out a few shortest jobs among all the processes from the secondary memory and send them to the main memory. From the main memory, again CPU scheduler needs to take a call, which is the next process to execute in the CPU. So that is the job of the job scheduler and the CPU scheduler. I hope I made my point very clear. So this job scheduler and CPU scheduler can also be called as a long-term scheduler and a short-term scheduler. Why? Because long-term scheduler meaning when the job scheduler executes for once, several programs will get transferred to the main memory. It won't need to execute again unless all these programs in the main memory get completely executed. So the job scheduler executes less frequently, very less frequently. But CPU scheduler needs to execute more frequently. How more frequently? The moment, let us say P1 is executing, when P1 is completely finished, immediately I need to select one more process. Let us say I scheduled PX. When PX is completely executed, completely finished, I need to select one more process. So CPU scheduler typically will execute in between the process, in between every pair of the process. When one process completely gets executed, I'm a CPU scheduler. When process P1 executes, I need to get into the CPU, execute for some time to decide what is the next process. So I just always am going to execute the moment one process gets finished. That's the reason why my frequency will be more than the job scheduler. Job scheduler frequency is very less. When the job scheduler gets into the CPU, it is going to pick up a few processes from the secondary memory and transfer them into the main memory. Its next turn will only come after all these processes in the main memory gets completely executed. I hope I made my point clear. Did I? Okay. Any doubts so far? Any doubts so far? Everyone? Okay. Now the thing is, let us understand what are the various process management activities. Operating system important job is to manage the processes. I'm the operating system. I need to manage several things in the system. What are my activities? First of all, I need to manage the processes. I need to manage the memory, which comes under memory management. Okay. I need to manage IO resources. In addition to all this, I also need to manage the processes. Did you get me? This is an important, job of the operating system. What is that? Managing the processes. So this is called a process management. What are the various process management activities? What exactly is the process? Let me explain you about the process again. The process is just nothing but a program which is in the execution, right? Okay, so when a process is created, it requires several resources. The resources should be provided. First of all, process should be created. So these are all the activities actually have to get handled by the operating system. So what are these, all the activities of the operating system with respect to a process? What are the, in other words, what are the various process management activities of the operating system? Let us understand. The first one is creating and deleting the processes. Malika, is the screen is not clear? Please let me know. Can somebody else confirm that the screen is clear or not? Okay, fine. Maybe in your streaming, sometime what may happen is due to the bandwidth fluctuations, sometimes screen may go blur, but that is not from my side. Okay, so if it is for more than one, please let me know. I will if there are any technical glitches from my side, I will be able to resolve them. It's clear, right? Very good. Now, what are the various process management activities of the operating system? Initially, first of all, it is responsible for creating and deleting the both process and the system process, user process and the system process. Okay, operating system is responsible for creating and deleting the processes. First of all, there is a need of executing a job. In order to perform the job, generally 10 to 12 marks. When the weightage is 10 to 12 marks. Lokesh, all these doubts I'll answer later, please. Okay. Do not interrupt in between because my mind goes off. Operating system first activity with respect to the process management is creating and deleting the process. When a job has to be carried out, with respect to the job, a process will be created by the operating system. Operating system is responsible for both creating and deleting. Why to delete a process? Upon its execution, upon its completion, an operating system also is responsible for deleting the process. Next one is suspension and resumption of a process. What is suspension? For example, there is Allu Arjun. This guy is scheduled. He's a process. And the operating system, I scheduled him. He went into the CPU for execution. For some time, he executed. But there comes one more guy. The newly incoming process now has more priority than ongoing process. What I need to do? I need to preempt this process, suspend the current process. When process P1 is executing and there arrives process P2 which has got more priority than P1, the process P1 should be preempted. The process P1 must be suspended to allocate the CPU to the incoming process which has got more priority than P1. Atre Chaudhary, already yesterday I've taken COA session, and GATE 2024 I'm not sure, but GATE 2025 I do have a plan. Which Atre Chaudhary, are you for GATE 2024 or 2025? Anyhow, please let me know. So operating system also is responsible for suspension and resumption of the process. When there comes a process arrives which has got more priority than the current ongoing process, immediately ongoing process must be suspended. The currently available process should be scheduled into the CPU. Yeah, Atre Chaudhary, we have, if you are in the second year, for the next, in this 2024, I will have many more sessions upcoming. I'll take the sessions for operating systems, computer architecture, and programming data structures, Verbal ability, digital logic. There are many sessions that are going to be organized and conducted by myself from Byjus exam prep. So stay tuned. Okay. So that's suspension and resuming the process. Third one is providing the mechanism for the process synchronization. What is process synchronization? This process synchronization will come after process communication. Some process would want to communicate with each other. Operating system generally keeps the process independent, makes the process always independent. But sometimes the process would want to communicate with each other. At that time, operating system should establish a communication in between those processes which would like to communicate. So operating system should establish a communication among those processes which want to communicate with each other. In order to have this communication smooth, operating system should synchronize the processes. This is an important aspect. Okay, I'm expecting a lot of questions from synchronization, which we're going to discuss in a short while. Okay, and providing the mechanism for the deadlock handling. Sometimes the system may enter into a deadlock state. What is the deadlock state? Simple. Number of resources are very limited, but number of the processes that are going to use those resources are more. At that time, there may be a deadlock. The biggest example for the deadlock is your traffic jam, because your resource is with another guy, another resource is with you. You want to go ahead on a road, you want to cross a crossroad, but the other side is completely full and this side is engaged by you and the other people. The resource which is required by the other guys, the opposite guys, are held by yourself. Resource which is required by you is actually being held by the other guys, which is now in a deadlock situation. Whenever operating system enters in a deadlock state, it should be able to resolve it. Okay, for which the deadlock will get handled. Operating system should provide an efficient mechanism for deadlock handling. So these are the responsibilities of the operating system, in which we're going to initially discuss about the process creation. Initially, we're going to talk about a process creation, process termination. How exactly the process is going to be created. Okay, here I'm going to take an example of a Linux operating system. In the Linux operating system, since it is my case study, since it is the freeware of the operating systems, I did not take Windows. Why? Because it's a shareware. We cannot research on the Windows operating system, but we can do every research on the Linux operating system. So our case study will always be Linux. In the Linux operating system, how a process will get created, how a process will get terminated, everything we are going to discuss right now. Okay, so what exactly is the process creation? If you ever want to create a process, first of all, you must have a parent process. A parent process will only be able to create a child process, for which, understand carefully, when the system is booting up, operating system initially will start its kernel portion, all the services will get loaded, then the system programs. What will get stored in the system programs? System programs meaning your compilers, your loaders, your linkers. Okay, all the system programs will get loaded in the system program section of the main memory. Then all the application programs will get loaded in the application programs of the section of the main memory. Then user space will get created. Am I clear? When the operating system is getting booted up, when the system is getting booted up, initially operating system will load its kernel portion in the kernel section of the main memory, followed by the system programs, followed by the application programs. Finally, user space will get created. Right after these operations performed, then operating system, every operating system will create something called a root process. What is the root process? Root process is the grandparent process. It is like Adam. Okay, we are the descendants of Adam according to the Christian Bible, right? So root process is Adam right now. Right from Adam, all the sub-child process will get created. From the root process, several system processes will get created. A tree of the process will get created. Then, whenever you try to execute a program, your user process will get created. Am I clear? So, a rough sketch will be like this. Initially, a root process, a process which is called a root, will get created by the Linux operating system, from which several system processes will get created in order to initialize the system. Then a tree of process will actually get created. Am I clear? So right then, after the total initialization process gets created, system will wait for the user to respond. Whenever user starts executing his programs, user process will get created. Am I clear? Then a total tree of the system process and user collection of system process and user process will completely get created. Am I completely clear? Do you have any doubts? I guess not. So understand this. See, now the thing is, I want to create a child. I'm a process. I want to create a child process. First of all, ever anybody wants to create a parent, or ever anybody wants to create a child process, you need to understand there must be a parent process. Only a parent process in tandem can create a child process, which is pretty similar to the real world scenario. Ever you want to give a birth to a baby, first of all, you need to understand there must be a parent. Parent can only give a birth to a baby. Did you get me? So understand. Forget about it. I just am creating a process. A process needs to be created. This is my task. Okay. I'm process PX. I want to create a child process. In order to create a child process, you need to understand. I need to execute one system function which is called fork. Okay. I will execute fork system call. System functions are called system calls. Okay. System calls are the smallest functions which are stored in the kernel portion of the main memory. When each function is executed, desired operation with respect to the function will be carried out. The fork system call outcome is to create a child process. Am I clear? I'm a process. When I ever want to create a child process, I need to make a call to the system function, which is otherwise a system call, which is called a fork. Am I clear? This is the initial thing that we need to understand. In the Linux operating system, when a new process has to be created, a parent process should be able to execute one system call called fork system call. When the fork system call gets executed, a child process will get created. Keep it aside. We are going to discuss a few things related to this. Okay. A parent process creates a children process, which in turn create other process, forming a tree of processes. What is the period of the child process? I'll let you know. I'll let you know. I'll come to this point. You need to hold on for some time. Okay. When the parent process creates a child process, of course, a child process will get created, a tree of process. Now, generally the process identified and managed via process identifier. Okay. Understand carefully. By default, I'm a child. My PID is just nothing but my parent's PID. Am I clear? My PID is just nothing but my parent's PID by default. But there is small exception for this, and we're going to discuss in a short while. Zinping dance, you need to wait for some time. Okay. So understand, I'm a parent. I've created a child. When a child is created, the child, in order to execute, it may require several resources. Every time a process is created, when a process is created, it requires several resources, right? Now I created a child process. The child process may also require several resources. What are the resources? How the resources can be shared? I'll tell you. When a child is created, there are several ways to provide resources to the child. Okay. The first one is parent and child will use all the resources. Sorry. The parent will allocate the resources to the child. Okay. Second thing is, parent is not responsible for allocating the resource to the child. The OS directly allocate the resources to every newly created child process. Are we clear? How the resources can be allocated? Understand, there are two ways. When a child is created, immediately it will ask for the resources. What are the resources? CPU time, memory space, IO device in the file system. It may require any of these resources, starting from the CPU's time. Okay. But who is responsible of providing these resources to the child? There are two ways. One is, when I created a birth, when I created a child process, I myself am responsible for providing the resources to the child. Second thing is, I'm not responsible. Operating system, he himself responsible to provide the resources for every child process. Generally, the second approach is not taken by any of the operating system nowadays. First approach is widely used because When the operating system allocates the resources, sooner or later operating system completely exhausts its resources, because there is no restriction on the parent process on the number of child process that can be created. Understand carefully. If somebody gives me a guarantee that resources can be given by somebody else for my child, obviously I can create as many childs as I require, right? Because my total work can be shared among the childs. Parent will not have any restriction or the imposition on the number of child that can get created. If the guarantee such that the resources can be provided by somebody else is given to me, so this is not practical. Operating system these days will never allocate the resources to the child. Rather, parent is itself responsible for providing the resources to the child. Are we clear? And the next thing is parent and child. See, in these two, parent will allocate the resources. The final one, parent and child share no resources, meaning OS will provide the resources to the child process. In the first two, parent and child share all the resources equally. In the second thing, of course, parent should be able to provide the resources to the child, but here a subset of the resources will be given. His resources are different, my resources are different, but his resources are a subset of my resources. Clear? Execution options, I will talk about the execution option in some time. Okay, let us see how a fork system call is going to work. Okay, understand carefully. Zinping dance, listen to me carefully. Now, I'm a process Anil. Okay, I want to execute and I want to create a new process. When I have to create a new process, I will execute a system call which is called fork. The intention behind the fork system call is to create a new child process. And when a fork is executing, it may have three possible outcomes. This fork system call, since it is a function, it is expected to return a value. The value can either be a 0 or can be 1 or can be any negative value. Generally, this fork can return a 0 value or any positive value or any negative value. So in order to simplify the things, we are assuming that the fork can return a 0 value, 1, positive 1 and minus 1. So what is it with this each case? What is with the 0? What is the meaning when fork returns 0? What is the meaning when fork returns 1? What is the meaning when fork returns minus 1? Let us understand. See. Are all of you with me or not? Sure, you're going to get a question tomorrow on this. For this, you need to be with me. All of you, please confirm that you're with me. Send an emoji, any emoji, whatever according to your likes. It's just I'm starting an important topic right now. Within 5 to 10 minutes, it will finish if you're with me. Yes or no? Are you listening or not? Somebody please answer. Am I audible and visible? No responses whatsoever? Very good. Okay. Now understand this. Now process Anil is executing in the CPU. This P Anil executed a system call called fork. Okay. Now let us say when P Anil calls a fork system call, executes a fork system call, let us say new process, child process being created, that is P, let us say ATR. Okay, P Anil, when it executes the fork system call, a new child process is created which is called PATR. Okay, so now what is it with this? Fork returns 0, fork returns 1 and fork returns minus 1. When fork returns 0, understand carefully, the creation of the child process is successful and now child is executing in the CPU. Am I clear? The creation of the child process is successful and child is executing within the CPU, not the parent. Where I am right now, I am in the CPU. During my execution, I executed a fork system call. The fork system call returns 0. Yes, it is successful. Creation of the child process successful. And what is it with this 0 then? This 0 stands for creation of the child is successful, and now child is executing within the CPU. Okay. Now what is it with this 1? Of course, creation of the child is successful, but parent is still executing in the CPU. Am I clear? -1 meaning simple. Creation of the child is failed. Process creation has been failed. So if the process still wants to create one more process, it needs to execute this fork for one more time. This is the thing with, this is the reason, this is the meaning of fork returning a 0, fork returning 1, fork returning -1. When fork returns 0, yes, child process created and now is executing in the CPU. 1 meaning child process created but parent is still executing in the CPU. -1 meaning no, the process creation is turned out to be a failure. Are we clear? That is it with this 0 and 1. Understand here. Somebody asked me, what is the PID of the child process? Generally, parent PID is equal to 1. Child PID is equal to 0. Now, by default, PID of the parent is also the PID of the child, but in order to differentiate in between these two processes, operating system should be able to allocate separate PIDs to these processes. But by default, during the process creation, my parent PID will also be attributed as to my PID. Am I clear? Somebody asked me, zimping dance. Did you understand this? Did you understand this or not? Malika Chaudhary, Lokesh, Atreyo, or zimping dance, you need to answer me. Did you completely understand this? 4 returns 0. Child creation is successful and child is executing in the CPU. 4 returns 1. Child creation is successful but parent is still executing in the CPU. 4 returns -1. Child creation is a failure. Next thing. Okay. Yep. I'll show you something here. Yeah. Look at this. Look at this. See, when the fork system call gets executed, when fork returns 0, child starts its execution. When child starts its execution, it will execute exec system call. How to calculate child fork? What is child calculate? We cannot calculate anything, sir. We don't calculate at all. What is calculating? I don't understand. You please need to rephrase your question. We don't need to calculate anything. We don't need to calculate anything at all. When fork is returns 0 or 1, child is successfully created. But when fork returns 0, child is successfully created and executing. When fork returns 1, child creation is successful but parent is still executing. Am I clear? When child is created, what it will do is, during its execution, first of all, child will start its execution with a exec system call. Exec system call. I'm a child. Let us say I'm a child. Okay. During my execution, I will start with a exec system call. When I do this, what will happen is, my parent resources will be allocated to me. My parent resources will be allocated to me, meaning, initially what will happen? My parent is residing in between 200 to 300 in the main memory. Now I'm a child. I need to store somewhere in the main memory where I can store in the same place as my parent. Okay. So in order to be stored somewhere in the main memory and also to utilize my parent's address space, initially what I'll do is I will execute something called exec system call. This exec system call will allow the child to use its parent address space. Whenever the ex, let us say I'm a child. Child started its execution. and the first statement to be executed is the exec system call. I started with the exec system call. The moment I executed this, immediately this total parent memory will be assigned to the child. This exec system call will allow the child to use the address space of its parent. Immediately, child process will be loaded in the place of the parent process. As simple as this. And when the parent process is executing, it will execute a wait system call. Let us say I created a child creation was successful. When the child creation was successful, should I execute anymore? I'll tell you what. Why child is created? A child is created for a purpose. And generally in the operating system, when a parent creates a child is created for specific purpose. So when a child is created, child should execute first. Child should carry out the operation that is assigned to it, and then after the operation is completely finished, child will terminate, and then only parent will continue. When I created a child, there is an assigned job. That assigned job must be performed by the child. Meanwhile, I need to hold myself for some time. After which, child will execute. Child will carry out the operation. Finally, after child completely finishes, then I will resume. So what I'll do is, meanwhile, when child is doing, when I'm executing, I will execute a wait system call. Parent will execute a wait system call. Wait system call meaning the operating system will not execute this parent process as long as the child process is running, because there is no meaning. When parent creates a child, parent should only execute after the child terminates completely, because there is a specific job assigned. After the job assigned which is completed, then only the parent is allowed to continue, for which parent will execute a wait system call. Wait system call will request the operating system not to execute parent anymore before child completely finishes. Did you get me? And finally, when the child is executing, of course, it starts with the exec system call, which allows the child to use the address space of its parent. And finally, when child completely terminates, it will execute exit system call. Am I clear? This exit system call, will allow the parent system call to resume again. When the child process executes a exit system call, the parent which was suspended earlier will be re-allowed to execute again, resume again. Okay. Now we will start with some questions, because for tomorrow's session, solving the questions is also important as equal as the theory discussion. Okay. We will start with the process creation, process deleting. Also, we'll discuss about the process scheduling. The first question is on your board, on your screen. Which of the following scheduling techniques cannot be implemented at a CPU scheduling level? I'll tell you. There may be several scheduling algorithms, right? There may be several scheduling algorithms. Shortest job first, FCFS, round robin, and none of this. Which scheduling algorithm cannot be implemented at the CPU scheduling level? I'll tell you. There are two schedulers in the system. First one is long-term scheduler or job scheduler. Second one is short-term scheduler or the CPU scheduler. Okay, what is the long-term scheduler? Long-term scheduler schedule the process from secondary memory to the main memory. Short-term scheduler schedule the process from main memory to the CPU. Are we clear? So understand the answer of this question. Understand how to solve this question. Which of the following scheduling techniques cannot be implemented at the CPU scheduling level? Which of these scheduling algorithms cannot be possible to be implemented at the short-term scheduler level or the CPU scheduler level? Is it FCFS? Is it round robin? Is it none of this? Or SJF? Understand? SJF is only a theoretical concept. SJF cannot be implemented as its definition in the CPU scheduling level. Why? Because shortest job first meaning. My scheduling algorithm should have every idea what is the length of this code. And are you listening? This is important. See, there is a process in the main memory. This process in the main memory, there is a process PX, PY. Okay. Now, I need to find out which is a shorter job among PX and PY. If I need to count the number of instructions, obviously PX or PY, let us say PX is equal to 100 instructions, PY is equal to 200 instructions. But for the plain looks, Px is expected to be shorter process than Py. But in general, Px may be longer than Py. I'll tell you why. When a process gets into the CPU, I already told you that it will execute only for some time in the CPU, then it goes to IO device, right? Did you understand? For an example, this Px has a printf statement. But before the printf statement, there are 40 instructions. After the 40 instructions, there is a printf statement in Px. But Py also has a printf statement, but only after 20 instructions. Are we clear? But for the plain looks, Px has total 100 instructions, Py has total 200 instructions. Which is the shorter job? Shorter job is 100 Px. But understand carefully, CPU scheduling algorithm should only take what is the next CPU burst time of the incoming process. It is not the total entire process length. It is only the length of the next CPU execution time of the incoming process. With that regard, in that aspect, Py is a shorter job than Px. But if I'm a scheduling algorithm, how would I know at which statement you do have a printf statement? At which line you have a printf statement? I got no idea, right? Do you understand this? So, SJF cannot be implemented at the CPU scheduling level. There is nothing as such SJF as a CPU scheduler level. Did you understand this or not? Look here. Atreyo mid-term scheduler, I will explain. Medium-term scheduler, I will explain. Do you understand this or not? Everyone. SJF is not possible to be implemented at the CPU scheduler level. Any doubts? You just can ask me. Everyone. Mallika, you there? Lokesh? Very good. Now, as you asked me, I'll tell you. As Atre suggested that, sir, there is also something called, medium-term scheduler, and what exactly is this? Okay, I will tell you. As I already told you, there is job scheduler. There is a CPU scheduler, long-term scheduler, short-term scheduler, and medium-term scheduler. What is the medium-term scheduler? Sometimes what will happen is, when the job scheduler schedules too many processes in the main memory will definitely have a threshold, right? Main memory, based on the size and multi-programming concept, main memory can accommodate only a few programs. There is a threshold point. Let us say main memory can support only 100 programs at a time at this point. But due to, some error, what if a job scheduler schedules more than 100 programs into the main memory? It is superficial. There is something more to add it to this. Something more, much more to add it to this. It is not the main memory size simply. It is also something called virtual memory space. There is a correlation between virtual memory space and the main memory space. Based on all these parameters, there is a threshold point how many processes can actually be scheduled into the main memory. Based on that, more or less some process will be allocated and will be stored into the main memory. But what if these processes are more? When the processes that are scheduled in the main memory are more, then definitely performance will get reduced. Page fault rate will occur. I am not talking about page fault rate, but I'll tell you simple calculations is, when more programs are in the main memory than the required ones, than the allowed ones, the performance will get reduced. When the more programs are stored in the main memory, performance will get reduced, right? Are we clear? So, in order to make this memory again free and increase the performance, get this performance back to the previous state, we will use something called a medium-term scheduler. This medium-term scheduler will remove a few processes from the main memory to increase the performance. When the too many processes are loaded into the main memory, performance will get reduced, which leads to something called thrashing. Thrashing meaning there will be more page fault rate. To reduce the page fault rate and to increase the system performance, I may use something called a medium-term scheduler. Medium-term scheduler may be employed in a system only to remove a few processes from the main memory, send them back to the secondary memory. Am I clear? So right, then what will happen is, when the few processes are removed from the main memory is expected to have only a few programs, a few processes. When the number of processes are sufficient to execute, again the performance will get increased. That is what the usage of the medium-term scheduler. Medium-term scheduler, the purpose of the medium-term scheduler is to remove a few processes in the main memory whenever there is a scenario called thrashing. Are we clear? Atreyo, or whoever you are. Okay, the next question. Did you understand this previous one? SJF cannot be implemented at the job scheduler level. Next question is, a scheduling algorithm assigns priority proportional to the waiting time of a process. Each process starts with a priority 0. The scheduler reevaluates the process priorities every t time units and decides the next process to schedule. Which one of the following is true if the process have no IO operation and all arrive at time 0? This is the question. Okay, so the question is, a scheduling algorithm assigns the priority proportional to the waiting time of a process. Every process starts with a 0 priority. The scheduler reevaluates the process priorities every t time units and decides the next process to schedule. Now, according to the details, which of the following option is correct? This algorithm is equivalent to the first come first serve algorithm. This algorithm is equivalent to the round robin algorithm. This algorithm is equivalent to the shortest job first algorithm. This algorithm is equivalent to the shortest remaining time first algorithm. Here you don't need to look at any other aspects. Here there is one statement in the entire question should attract you firmly at the first place. What is that? The scheduler re-evaluates the process priorities every t time units, meaning there is a time quantum t. When we are going to use a time quantum t, a stipulated time quantum will be assigned to a process only in round robin scheduling algorithm. In round robin scheduling algorithm, every process will be given some t time units, which is always fixed. Every process will be assigned with a t time quantum. I hope I made my point clear. This is a round robin scheduling algorithm. What is this? Option B. Clear or not? Okay. Are we clear with this question? Whenever you see a scheduling algorithm uses priorities based on time quantum, this is just nothing but a round robin scheduling algorithm. Okay. Next thing is, consider three processes P1, P2 and P3 shown in the table. This is the process P1, this is process P2, this is process P3. Process P1 said to have arrived at 0, process P2 said to have arrived at 1, process P3 said to have arrived at 3. Time units that are required by this process are 5, 7, 4. Okay. So the question is, what is the completion order of these three processes under the policies FCFS and round robin 2? In which order the process are expected to be completed? The order is A, B, C, D. Obviously understand, FCFS always goes with the arrival order. The order of arrival will also be the order of departure, right? FCFS meaning first come first serve. P1 will be executed first, P2 will be executed next, P3 will be executed at the third place. There is no difference in there is no disturbance in these positions of their execution. But round robin, what is RR2? Round robin 2 meaning every process will be given a stipulated time quantum which is equal to 2 clock cycles. After 2 clock cycles, no matter, regardless of either this is finished or not, the process is preempted, right? This is what round robin, what you learned. Am I clear or not? Yes or no? So understand which is the correct order of execution of this process with respect to FCFS and round robin 2. Okay, FCFS is always P1, P2, P3. There is no doubt about it. But RR2 meaning how this is going to work. Okay, understand carefully. This is my main memory. This is main memory. I have 3 processes, right? I will create 3 slots for this processes. This is the first slot, this is the second slot, and this is the third slot. Understand carefully. Now the thing is, this is the CPU. Okay. Now at the time 0, P1 arrived. Am I right? All of you please respond. At time 0, P1 arrived. At time 0, when P1 arrives, there is no other process in the system. So obviously, P1 enters into the system at the 0th clock cycle. So I will erase it from the main memory. Okay. Main memory, all the slots are free because the only process which said to have arrived already got into the CPU. Now at time 0, the process which have arrived into the main memory has already been sent to the CPU. Now understand. At time quantum 1, what happened? P2 has arrived. P2 has arrived at time quantum 1. But at time quantum 1, what exactly is happening? P1 is already executing in the CPU. P2 has arrived. As the main memory is completely free, P2 will occupy the first slot in the main memory, which is also called as the ready queue. In the ready queue, first slot will be occupied by the P2 and P1 already is in the CPU for execution. Now understand carefully. What is time quantum? The time quantum is 2 clock cycles. Okay, so every process is expected to be in the CPU only for 2 clock cycles, after which every process should be preempted. Now, according to that rule, P1 is going to leave the CPU at the second clock pulse. At the second clock pulse, who is available in the main memory? Only available process in the main memory at the second clock pulse is P2, and the process which is in the CPU is going back to the main memory. So at the end of the second clock pulse, what is happening? P2 will go back, will go to CPU and P1 will go back to the main memory. P1 will be here and P2 will be here. Because at the second clock pulse, P3 did not arrive yet. Am I clear? So initially P1 started followed by P2. Then there comes one more process P3. But when the time process, by the time process P3 comes, first slot of the ready queue is already full. So P3 will follow P1 occupying the second slot. I hope you got the point. This is the important thing to understand. Now when P2 comes back, P2 will be followed by P1 and P1 will be followed by P3. Okay, and P3 will be followed by P2 again. Did you understand carefully? Did you understand this? Initially P1 and then P2, but when P1 is going back, there is nothing, there is nobody in the main memory. So obviously, like a king, P1 is going to occupy the first slot in the main memory in the ready queue, then followed by P3, because P3's arrival time only is at the third clock pulse. So at the fourth clock pulse, P2 go out, P2 will be here. Did you understand? Then P1 gets in, P3 gets in, P2 gets in, then P1 gets in, P3 gets in, P2 gets in. So in round robin 2, the order of execution will be P1, P3 and P2. Yeah, I'll explain. Sure, I'll explain it again. I'm sure some of you people had a slightest confusion in this. I'm going to make it completely clear. Okay. All of you, for which I want you people to be with me. Okay. I will name this process initially. Yeah. Okay. I will name this process as Anil. Anil is the first process, followed by Mallika, followed by Atreya, ATR. Okay. Anil is P1, Mallika is P2, Atreya is P3. Okay. Now understand, this is an ATM machine. Okay. In this ATM machine, you are allowed to be in only for 2 clock cycles. After 2 clock cycles, you need to join back in the line. Am I clear? Are we clear? Say yes or no. I do have a queue right in front of the ATM machine. I do have a single ATM machine. The only rule is to use the ATM machine for 2 clock cycles at a stretch. Not more than 2 clock cycles at a stretch can be allowed to anybody. Are we clear? So there are 3 people. One is Anil, one is Malik, and one Mallika, and one more is Atreya. Did you get me? So Anil arrived into the queue of the ATM machine at a 0th clock pulse. So Anil is the first guy to enter into the queue. The moment Anil enters into the queue, he found that there is nobody in the ATM. He directly can make his way into the ATM. Am I right? At the 0th clock pulse itself, he directly can walk into the ATM machine. Yes or no? Anil can be here. Now the Anil, since he already got into the ATM machine, this queue is said to be empty. Am I right? Okay. Now what happened? At the first clock pulse, Anil is given 2 clock pulses, right? Yes or no? Anil will be in the ATM machine for 2 clock pulses. Now, at the first clock pulse, as Anil is already in the ATM machine, one more guy entered. That girl is Mallika, entered into the queue. The queue is free. The only guy who entered into the queue is Anil, already went into the ATM machine. Now, second guy, who happened to be a girl, Mallika, will stand right in front of the ATM machine at the first clock pulse. At the first clock pulse, Anil is in the ATM machine. He is consuming his time. He is utilizing his ATM time of 2 clock cycles, and Mallika is in the queue right in front of the queue at the first slot of the queue. Now understand, Anil, at the second clock pulse, what will happen to Anil? Anil will be interrupted. He cannot continue anymore. More than 2 clock cycles, no process is allowed to continue within the ATM machine, which is said to be happened to be our CPU right now. Now Anil is leaving the ATM machine. When Anil leaves the ATM machine, who is there in the queue? There is only one guy. At the second clock pulse, process P3 Atreya did not arrive, right? So when Anil goes out, he will stand in the first slot of the ready queue. The Mallika goes in, Anil will go out. At the end of the second clock pulse, the scenario will be Mallika here, and Anil will go back, since at the end of the second clock pulse, third process has not arrived yet. Am I clear? So it starts with the execution of Anil, followed by Mallika, and now Anil goes back at a second clock pulse, but the third clock pulse, Atreya arrived. Okay, at the fourth clock pulse, what will happen? Mallika will come out and will occupy the third slot. Am I clear? Mallika will be here. The moment Mallika finishes, Anil will enter, followed by Atreya, followed by Mallika. I hope you got the point. The order of completion is the order of execution, which is just nothing but initially Anil, followed by Mallika, followed by Anil, followed by Anil, Mallika, Anil, again Mallika, followed by Atreya. Hold on, just a minute. What is it? And Anil goes back. Mallika will be here. Yeah, order is Anil, Atreya, Mallika. Because the moment Mallika enters, Anil will go and occupy this slot. So order of the execution will be Mallika, Anil, Atreya, Mallika. So order of the execution will be Anil, Atreya, Mallika. Are we clear? Everyone. Are we clear? Any doubt, sir? Malika ma'am, and there is Jayesh, Lokesh. Are we clear with this? Everyone? Okay then. An operating system implements round robin with a time quantum of 5 milliseconds to schedule the process. If there are 6 processes in the system, what is the waiting time of each process for its next turn? This is the question. After P2 once. After P2 once, what does it mean? What is it question, sir? Yeah. Anil is the first process. When Anil goes into the CPU, Malika enters. Malika is the second process. After Malika, Anil will go again. P1 will go again because Anil will stand right in front of the ready queue, right? After the second process, again comes the first process because third process did not arrive. By the time second process finishes its first turn, third process did not arrive. So, first process will start again. So, P1 followed by P2, again followed by P1, followed by P3, followed by P2. P1, P3, P2 is the order of the execution. P1, P3, P2. Are we clear? Option C is correct. An operating system implements round robin with a time quantum of 5 milliseconds to schedule the process. If there are 6 processes in the system, what is the waiting time of each process for its next turn? Time quantum of 5 milliseconds to schedule the process. If there are 6 processes, could you please let me know what is the answer for this? What is the answer for this? What is the answer for this? The answer is the minimum of 25 milliseconds is the correct answer. Why? Because see the total 6 processes, 6 into 5 is equal to 30. When there is no process in the system, each process which takes 5 milliseconds for its next turn, the total expected runtime of all the process will be 30 seconds as a whole. But when process arrives, when this process arrives, the other process total execution time only will be 25 milliseconds. Am I clear? So the last process, any process, needs to wait for its turn for 25 milliseconds, not less than 25 milliseconds. Meanwhile, there is some overhead time called context switching time. So context switching time will be an added time. What is the context switching time? When a process is going out, one more process is incoming, the data has to be switched from the CPU to the main memory of the process 1 and process P2, which is called the context switching time. This context switching time will be additional overhead to the regular waiting time. So the process waiting time will, Atreyo sir, 5 milliseconds. Of course, 5 into 6 is equal to 30. But when one process gets in, remaining process waiting time will only be equal to 25, right? Did you understand? I am the final process. I am the 6th process. For how much time? For how long I need to wait? 5 5s are 25. After the 25th clock cycle, I will enter, right? You got my point? My waiting time should only be the amount of the time which is required by the other process to execute. The other process are only 5 except me. 5 into 5 is equal to 25. The total waiting time of any process is the total time required by the other process only. Not exactly 25, sir. Exactly 25 cannot be possible. I already told you, Jayesh. See, the minimum waiting time is 25 milliseconds. See, understand. I am in the CPU. Jayesh, you are in the main memory. After 5 milliseconds, I will come out. You will come in. We are only the 2 processes. Let us say you waited for 5 milliseconds. Is it practical that you enter into the CPU exactly at the 6 o'clock pulse? No. I will let you know why. Because there is some more time called context switching time. When I am leaving the CPU, I need to collect my baggage. There are some values in the CPU. I need to collect my values from the registers. I need to transfer them back to the main memory. At the same time, you are entering in. Your values must be collected from the main memory and transferred to the CPU, which takes some significant time, can otherwise also be called as context switching time. In addition to the regular waiting time, context switching time will be added more. So, the minimum waiting time is 25 milliseconds plus context switching time. Are we clear? Jayesh? Yes or no? Jayesh, you need to answer. It is minimum of 25 milliseconds. Not more than 25 milliseconds cannot be the answer at all. Everybody should answer this. This will solve important questions, important because we are running out of the time. Hello, Sachin. Yeah, I'm in the class. Anything important? Yeah. Okay. Yeah. So let us solve this question. Next question. Consider the CPU intensive process with which require 10, 20, and 30 time units and arrive times are 0, 2, and 6 respectively. How many context switches are needed if the operating system implement the shortest remaining time for scheduling algorithm? Do not count the context switches at the time 0 and at the end. Understand how this can be solved. This is the Gantt chart. This is the Gantt chart. In the Gantt chart, we need to plot the 0th clock pulse and the final clock pulse. Final clock pulse is 0 plus 2 is equal to 2, 2 plus 6 is equal to 8. In order to finish all the process, I require 8 clock cycles. Are we clear? Now the thing is, CPU intensive process arrive at times 0, 2, and 6 respectively. Okay. Now at time 0, what has arrived? The process P1 arrived. Okay. Process P1 arrived. At time 0, what have arrived? Process P1 arrived. P1 enters into the system. Okay. When P2 arrives at the second clock pulse, P1 execution status will not change because P1, according to the scheduling algorithm, is the shortest remaining time process. Hold the shortest remaining time. So P1 is allowed to continue. Right then, when P1 comes out at the 10th clock pulse, what will enter? P2 enters into the system. When P2 finishes at the 30th clock pulse, because P2's total execution time is 20 clock pulses. So when the P2 finishes, P3 enters. Okay. When P3 will finish, the P3 will finish at P3 is 30, right? 30 plus 30, this is 60. Okay. So the total Gantt chart time is the total required time of all the process. It is not 0 plus 2 plus 6, but it is 10 plus 20 plus 30. Bigger pardon, earlier I considered that 0 and 2 and 6 are the burst times. These are not the burst times, these are the arrival times. So P1 will enter first, followed by P2, followed by P3. Now how many context switches? Context switches we need to count only in between the processes, not in the beginning or not in the ending. So we need to remove this and we need to remove this. So when P1 switches to P2, there is a context switch. When P2 switches to P3, there is one more context switch. The total number of context switches in this case is equal to 2. Are we clear? Context switches meaning when a process goes out and one more process is incoming. We cannot consider the first entry and the last exit. So first entry we have removed, last exit we have removed. So the separations will be only 2 at the 10th and 30th clock pulses. The total context switches are equal to 2 only. Are we clear? Yes or no? Consider three processes all arriving at, next question is, did you finish with the previous question? Are we done? Everyone? Jayesh, Atreyo, Lokesh, are we completely done with the previous question or not? Okay. The next question is, consider three processes all arriving at time 0 with a total execution time of 10, 20 and 30 units respectively. Each process spends the first 20% of the execution time doing IO, next 70% of the time doing computation, and a final 10% of the time doing the IO again. Okay, the operating system uses shortest remaining time compute time first scheduling algorithm and schedules a new process either when the running process gets blocked or on IO when the operating system uses the shortest remaining time compute time first, okay, and schedules the new process either when the running process gets blocked on an IO or when the running process finishes its compute burst. Assume that the IO operations can be overlapped as much as possible. For what percentage of the time the CPU will be idle? This is the question. It's a very simple question, only it's a lengthier question, but do not get dissed. It's a very simple question. Only thing is you should be able to resolve this the conflicts in the data that is being provided. So for which I need to draw a table. How many processes? There are three processes. Process, initially every process will start in IO, followed by CPU burst, followed by IO again. For the first process P1, what is the total time requirement? Total time requirement is 10 milliseconds. In the 10 milliseconds, what exactly will happen? Initially, every process spends the first 20% of the execution time doing IO, meaning for the first 2 seconds, it will go to IO. Okay. Next 70%, it will execute within the CPU. That is 7. Okay. 7 clock pulses, it will be in the CPU. And then remaining 10% again doing IO again. So, total 10 clock pulses of the P1 will be spent 2 clock cycles in the IO first, 7 clock cycles in the CPU next, followed by 1 clock pulse in the IO next. When it comes to the P2, P2's total time requirement is 20 clock pulses. In the 20 clock pulses, first 10%, 4 clock pulses will be spent in the IO, and the next 30%, meaning 20 clock pulses, right? Next 30%, total 20 into 6 clock pulses. Just a minute. 2, 7, 1. Yeah, this is 14. 2. Okay. So this is the thing. First 10% of 20 will be in the IO. Next 70% in the 20, which is the 14 clock pulses in the CPU. Next 10% of 20, which is 2 clock cycles in the IO again. When it comes to P3, total time requirement of P3 is equal to 30 clock pulses, in which 20%, that means 6 clock pulses will be spent in IO, and again 70%, 70 in 30 will be equal to 21 clock pulses in the CPU, and finally 10% in 30 will be equal to 3. Okay, total 30. So this is the time requirement for the various operations of this process. Now the question is, for how much percentage of the CPU will get wasted? For what percentage of the time does the CPU will be idle? So we need to calculate the percentage of the CPU wastage. Simple. How will we be able to calculate it? Okay. Now initially which process starts? Obviously process P1 starts. Okay. When process P1 arrives at time 0, Does it enter into the CPU directly? No, it will not enter into the CPU directly. And at the same time, you need to understand all the process said to have arrived at the first clock pulse itself, meaning in 0 itself, P1 enters, P2 enters, and P3 enters according to the question, all arriving at time 0 with a total execution time 10, 20, 30. But when P1 arrives, it goes to the IO for 2 clock cycles. So initially, for the first 2 clock cycles, there is nobody in the CPU because in the first 2 clock pulses, P1 is in the IO, P2 is in the IO, P3 also is in the IO. But the first guy who returns from the IO is P1 because P1 is going to only spend 2 clock cycles in the IO. So P1 returns at a second clock pulse from IO. So P1 will come back to the CPU at a second clock pulse and P1 will execute for 7 clock pulses in the CPU. So P1 will execute from 2 to 9. 2 to 9 is equal to 7, right? For these 7 clock pulses, P1 executes within the CPU. Right after P1 finishes, P2 enters into the CPU because P2 already finished with its first IO. The IO is 4 clock pulses. IO period of initial IO period of P2 is 4 clock pulses. Obviously, P2 by the time P1 comes back is readily available. Hello. నేను బిజీగా ఉన్నానండి మళ్ళీ చేయండి థ్యాంక్ యూ ఓకే then P2 enters. P2 is going to spend for 14 clock cycles in the CPU. So 9 plus 14 is equal to 23. Then P2 goes to IO. P1 goes to IO at 9th clock pulse. Final IO of the P1 will be at the 9th clock pulse. P2 will go to IO at the 23rd clock pulse. And P3 comes into the CPU. And P3's burst time is 21 clock pulses. So P3 will be in the CPU in between 23 to 21. 23 plus 21 will be equal to 44. Okay, at the 44th clock pulse, sorry, 23 plus this is 44. At the 44th clock pulse, P3 will go out. But after P3 goes out, for how much time P3 is going to spend its IO? So for 3 more clock cycles, this is 44 plus 3 is equal to 47. So for the first 2 clock pulses, last 3 clock pulses, CPU is idle. Are we clear? See, initially for the first 2 clock pulses, there is nobody in the system. So 7 plus 14 plus 21. Next, P1 enters, will consume 7 clock pulses. 2 to 9 is 7 clock pulses. Again, P2 enters. After P1 finishes, P2 enters. At this time, P1 goes to IO. P2 enters. P1 is going to spend 14 clock pulses between 9 to 23. Then P2 goes to IO. Then P3 comes in. P3 is going to spend in between 23 to 44, which is 21 clock pulses. Then at the 44th clock pulse, P3 goes to IO. Did you get me? When P3 goes to IO, it is going to spend the remaining 3 clock pulses at the IO. So the total execution time is 47 clock pulses. Out of 47 clock pulses, the total number of wasted clock pulses are equal to 5. Okay, 5 in 47 will be 10.6. For 10.6% of the CPU time idle. The CPU for the 10.6% of the CPU time, there is nobody is in the processor. Did you understand this? Or any questions? Did you understand this or not? Everyone? Or should I repeat this? If you do have any doubts, I'll explain you for one more time. Everyone? Sure, okay, fine. I will repeat. A few people did not understand this. I will explain again. Understand all of you? This is the CPU consumption, okay? Gantt chart meaning it is the CPU consumption. Okay. Now process P1. P1 execution time is 10 clock cycles, but it must be divided into 2, 7, 1. P2 must be divided into 4, 14, 2. P3 must be divided into, I'll show you right now. You don't need to worry. I showed it already. I don't know why you missed. Again, I'll show you. This is P1. This is P2. P3 is first 20 clock pulses, right? 6, 21 and 3. Okay. P1 required 10 clock pulses. P2 required 20 clock pulses. P3 required 30 clock pulses. Understand carefully what is IO. When I go to an IO device, I need to perform some IO operation in the IO device. Understand carefully. Here, all the IO operations, somewhere it is given that all the IO operations can be overlapped. Meaning, when I go to an IO, my operation will not be overlapped to any other process. Meaning, system sufficiently provided the IO devices. So when I go to an IO device, I need not wait for anybody. If I go to the printer, printer is exclusively available for me. My IO operation can be performed in parallel to the other IO operations. Are we clear? Sir, IO time for the P2, P3 in Gantt chart. Sure. Atreyo, listen to me carefully. Okay. Now, everyone, P1, P2, P3. Why did not I show for P2 and P3? That is your question, right? I'll tell you this is not needed for the CPU burst time. Initially, P1, of course, P1, P2, P3, everybody arrived. But P1 is going to spend 2 clock cycles in IO. P2 is going to spend, P1 is going to spend, yes, 2 clock cycles in IO. P2 is going to spend 4 clock pulses in the IO. P3 is going to spend 6 clock pulses in the IO. Okay. But you will understand why I did not show in the first place. After, who is going to return back to the CPU? Obviously P1, right? P1, after spending for 2 clock pulses in IO, it will return back to the CPU and it will execute for 7 clock cycles in the CPU. Am I right? Did you get it? When P1 comes back, P2 and P3 are still in IO. And I don't need to show them because Gantt chart is only the CPU consumption time. Did you get it? So by the time P1 comes back at the 7th clock pulse, at the 2nd clock pulse, P2 and P3 are still in their IO. Now P1 enters here. This is the total CPU consumption time. That is 0 to 2. There is nobody in the CPU. This is the only CPU's consumption time. Am I clear? Am I right? So obviously, I will only show here the CPU consumption. So for how much time P1 is going to spend within the CPU? 7 clock pulses. That means till 9th clock pulse, P1 will execute in the CPU. When P1 leaves, it will go to perform some IO operation. Did you understand? That is, for how much time? It is going to spend 1 more clock pulse. But I don't need to show this 1 more clock pulse in the CPU because this is only CPU consumption time, sir. But the moment P1 leaves, obviously P2 enters. Because the moment P1 leaves, it will be 9th clock pulse. By the 9th clock pulse, P2 and P3 are already available. So P2 will enter into the system. P2 for how much time? For 14 clock pulse will be spent in the CPU. For 14 clock pulses, P2 is going to spend, P2 is going to be in the CPU. So 9 to 14 is equal to 23. 9 plus 14 is equal to 23. At 23, P2 will come out, will go to IO. For how many clock pulses? For 2 clock pulses, it will go to IO. But this is irrelevant. They are performing some IO operation other than the CPU. Do we need to consider? No, I don't need to. Next, P3 comes in. For how much time it is going to spend within the CPU? 21 clock pulses. So P3 is going to spend 23 plus 21, 44. At 44, P3 will leave the system. But in order to finish the total processes, when P3 goes out, P3 is going to finish its IO operation at by spending 3 more clock pulses. Did you get me? So after the 44th clock pulse, P3 needs 3 more clock pulses to perform IO. But by the time P3 comes out, P2 finishes and P1 finishes. Did you understand? By the time P3 comes, there is nobody left in the system. Only P3 will finish finally after spending 3 clock pulses in the IO. So initially for the first 2 clock pulses, CPU will be idle, and the final 3 clock pulses, CPU is idle. Remaining all CPU is engaged. Did you get me? So in the total execution time, which is equal to 47, for the first 2 clock pulses, CPU is idle. For the first final 3 clock pulses, CPU is idle. So out of 47, 5 clock pulses, for the 5 clock pulses, CPU is idle. So what is the percentage? Percentage is 10.6. I hope I made my point very clear. Did I? Did I make it clear? Yes or no? Any doubts? Very good. Here, the next question is, a uniprocessor computer system only has 2 processes, both of which alternates 10 milliseconds CPU burst time and 90 milliseconds IO burst. Both the processes were created nearly at the same time. The IO of both processes can be proceeded and can be proceeded in parallel. Which of the following scheduling strategies will result in the least CPU utilization? First is first come first served, shortest remaining time first, static priority scheduling with the different priorities for the 2 processes, round robin scheduling with a time quantum of 5 milliseconds. This is the question. Okay, the last question that we're going to solve, because the time is, I thought of even covering, but 2 hours are just only spent for, the process scheduling. I request you people to go through my previous synchronization videos. I last year, I guess nearly 3 to 4 synchronization videos have been made. I request you people to go through the synchronization videos with the PYQs, all the PYQs covered. So I want you people to go through those videos before you go to the exam tomorrow, because synchronization, I'm expecting a few questions. Okay. But how did you get 43 as the total? Yeah, total execution time was 43 only, right? See, it starts from 0 and enters at 2 and total 47. Look at this. For what percentage of the time does the CPU remain idle? At the arrival, understand carefully. There is a simple catch in that. I need to explain you that. See, generally, any process will start with the CPU burst, followed by the IO burst, and come back to the CPU burst, we'll go back to the IO burst, come back to the CPU burst, we'll go back to the IO burst, and finally with one final CPU burst, any process will terminate. But this is purely hypothetical question. He states that the process is starting with the IO burst and goes to the CPU and finally finishes with this IO burst, which is purely hypothetical. Here, processes are starting from IO burst. Did you get it? So that means when the process gets in, initially as they are going to IO, CPU time will be idle, right? He is just asking to calculate idle time when the processes are executing. Did you get it? So initially, for the first few clock pulses and the final few clock pulses, CPU will be idle as the processes are executing. In the total time of execution of the processes, how much time of the CPU is kept idle? That's the question. Total time includes both IO burst and the CPU burst, right? So initially for the first 2 clock pulses, when the processes are executing in their IO, CPU is idle. For the final 3 clock pulses, when the processes are executing in their IO, CPU is idle, right? But the total execution time starts with 0, ends with 47. Am I right? Yes or no? Total execution time is 40 seconds, right? Sorry, 47 milliseconds, right? Atreyu. That's it. Yeah. A uniprocessor computer system has only two processes, both of which alternates 10 millisecond CPU burst with 90 milliseconds IO burst. Both the processes are created nearly at the same time. The IO of both processes can be proceeded in parallel. Which of the following scheduling strategies will result in the least CPU utilization over okay, just a minute. Just a minute. Yeah. Let us start this. Uniprocessor computer system has only two processes, both of which alternates 10 CPU milliseconds, 90 milliseconds. Both processes are created. Which of the following scheduling algorithm? Okay. The thing is, there are two processes. One is process P1, one more is process P2. Okay. Both processes alternate 10 millisecond CPU burst with 90 milliseconds IO burst. So initially, the process P1 will execute for 10 milliseconds in the CPU and 90 milliseconds in the IO. For process P2 also, for 10 milliseconds it will be in the CPU, for 90 milliseconds it will be in the IO. Okay, the question is, which of the following scheduling strategies will result in the least CPU utilization? Meaning the worst CPU utilization, not the best scenario. He is asking for the worst scenario. Which of the following algorithms will incur the worst CPU utilization? First come first serve scheduling algorithm. Let us understand P1, P2. P1 is the first one, P2 is the next one. Let us say at time 0, P1 enters. When P1 enters, P1 is going to spend only for 10 milliseconds, then it goes to IO. Then P2 enters. When P2 enters, P2 will execute for 90 milliseconds, P2 will execute for 10 more milliseconds and it will go to IO. Then P1 will return back. When P1 will return back? P1 will return back at after 90 milliseconds, meaning P1 will come back at 100 milliseconds because it is going to spend 90 milliseconds in the IO. So P1 will come back at 100 milliseconds. Am I clear? Then P1 will leave at 110 and P2 will come back at 100 because P2 went to IO at the 20th millisecond because P2 is going to spend only for 10 milliseconds. P2 went to IO at the 20th millisecond. So since it is going to spend 90 milliseconds with the IO, P2 is going to return back to the CPU at the 110th millisecond. So P2 will come back. P2 will leave at 120. This is going to be done all the time. So for how much percentage of the CPU is idle? For how much percentage of the time CPU is idle? In between 20 to 100, total 80. So total CPU wastage is 80%. CPU time wastage is equal to 80% in this scenario. When it comes to the first come first serve, the total wastage is 80%. What about shortest remaining time for scheduling algorithm? There is no meaning of shortest remaining time for scheduling algorithm because there is no shorter, because both CPU time is equal, also the IO time also is equal. So there is no meaning for shorter remaining time for scheduling algorithm. So this is not possible because both process CPU burst time and the IO burst time are exactly equal. Static priority scheduling with the different priorities for the two processes, meaning he is asking you to give the different priorities to the processes. Even if you give the different priorities, let us say P2 will execute first. I have given priority to P2 than P1, but still it will be the same, right? The amount of the time that is being wasted by the CPU will still be 80 milliseconds, right? CPU wastage time will not be altered even if P2 executes first. P2 and P2 will have the same aspects and same parameters. Even if P2 executes first, P2 is going to execute only for 10 milliseconds in the CPU. Then it will be P1. Still 80 milliseconds will be the time wastage. So for the first three, 80% will be the time wastage. And we need to calculate for the round robin scheduling algorithm with a time quantum of 5 milliseconds. We will see how it's gonna work. Initially at time 0, P1 enters. But here round robin 5, meaning P1 will be printed at the 5th clock pulse. So P1 goes back and it is waiting for its turn to enter into the CPU again. Then P2 will come. P2 will be printed at the 10th clock pulse. When the P2 gets printed, P1 will come back. P1 will come back and will go to the IO. At which clock pulse? At the 15th clock pulse, because every process P1 and P2 needs to spend for 10 milliseconds in the CPU. So that means P1 finishes with its first CPU burst at the 15th clock pulse. At the 15th clock pulse, P1 is expected to leave. P1 leaves the CPU and P2 comes back. P2 leaves the CPU at the 20th clock pulse. Did you understand? But when P1 is going to come back? P1 is going to come back after 80 clock pulses. 15 plus 80 is equal to 105. So P1 is going to return at 105th clock pulse. Am I clear? 15 plus 80 is equal to 15 plus 90 is equal to 105th clock pulse. I hope I made my point clear. So P1 will return back at 105 and P2 will return back at 110. So for how much percentage of the CPU is wasted? It is 20 to 105. A total of 85 milliseconds gets wasted. That means earlier the total CPU wastage time was just 80. Now the total CPU wastage time is 85. So in between 80 and 85, 85% is more, and this is the least CPU utilization, meaning for more time CPU is idle. So option D is correct. The question which is asked is for how much time least CPU utilization time. Least CPU utilization time. The total wastage time of the CPU is, for the first three cases, is 80. The wastage time of the final case is 85. So option D is the correct answer. Are we clear? Yes or no? Should I start the stream again? I started the stream, but what about this studio? Studio also, I need to start the stream and start the stream again. Studio already is running. Should I stop it here also? Hello? Should I stop here also in this studio? Hello. Anuj, am I audible? Thing is, my OBS is crashed right now. I stopped OBS and restarted OBS. Uh, I start streaming again. I करे थे. वहाँ पे भी OBS में okay. Again, I need to enter those things. Okay, and the server and stream key again I need to paste. Okay, okay, sure, sure. Okay, but I don't need to copy the. Yeah, hello everyone. There is a technical glitch. Due to the technical glitch, I couldn't, hold on for a while. There are a few, things disturbed. Something has been crashed, so I couldn't take this past 10 to 15 minutes. But whatever, with which we have come to an end of this session. I want you people, I want you people to go through my previous synchronization classes for at least 10 to 15 minutes because I'm expecting a lot of synchronization questions this time. And last year I covered, I've taken almost, 2 to 3 synchronization sessions for YouTube. I want you people to access them and you'll be able to get a lot of PYQs from them. I want you people to solve as many PYQs as possible for this GATE 2025 because in 2025 I'm expecting operations on the process on fork at least and scheduling, Gantt charts, and finally the synchronization questions in operating system. I want you people to go through my previous sessions of synchronization in which I explained a lot of PYQs and prepare. And I hope this session is very useful for you guys. I'm sure it is. And I hope and I'm sure you're going to give your best in tomorrow's exam. The rest is left to the God, but I'm sure you just are going to do miracles in the GATE exam by attaining a very good rank indeed. With which we have come to an end of this session. Thank you so much, and that's it for the session.